Welcome back, and here's some more trig identity substitution integrals. So you can title your page More Integrals. Using trig identity substitution. So this is day 2. Okay, so yesterday we did integration using those Pythagorean identities. Today we're going to use some of the double angle identities. Now these people aren't as familiar with, but you should have all seen them before. If you remember, the double angle identities are sine of 2x. Remember what that is? 2 sine x cosine x. You could see how that one would be used pretty easily, right? If you had the integral of sine of 2x, you could then do a u sub, let u equal sine of x, and you've got cosine of x right in there. Okay, we've got cosine of 2x. Now cosine of 2x had options. Cosine of 2x was cosine squared of x minus sine squared of x. But then you could also write cosine of 2x using just sines or cosines, because now you can use Pythagorean identity substitutions. Okay, remember sine squared x is 1 minus cosine squared. So if I plug in 1 minus cosine squared here, I'd have cosine squared minus 1 plus cosine squared, so that would end up being 2 cosine squared of x minus 1. And similarly, we could write it with just sines. If I replaced cosine squared with 1 minus sine squared, I'd have 1 minus sine squared, which is 1 minus 2 sine squared of x. Now these last two I want to look at again. These are the ones you would have done a lot in pre-calc, something you probably haven't done too much. What if I wanted to solve this equation right here for cosine squared? So if I get cosine squared of x alone, what would that equal? Well, I could add the 1 over here, so it'd be cosine of 2x plus 1, and then I would have to divide by this 2. Okay, so in other words, I could also think of this, just because constants in integration are easier if they're pulled out front, as 1/2 times cosine of 2x plus 1. Okay, so cosine squared of x can always be replaced by that. I'll show you why that matters later. Similarly, I could solve for sine squared in this last equation here, right? I've got a negative here. So if I'm going to want sine squared of x alone, I would have to subtract this 1 over. So I'd have cosine of 2x minus 1. Then I would have to divide by negative 2. Or, if I play around my negatives a little bit, we could say this is equal to 1 minus cosine of 2x over 2. Right? I could put the negative through on the top instead of on the bottom. So what I wanted to say, this is the same as 1/2 times 1 minus cosine of 2x. And we can always replace sine squared of x with that. Okay, so now I have ways I can replace cosine squared of x and sine squared of x. New ways that I can replace them using something that I can take the integral of, because these things in red are easier to take the integral of. And when I say that, I should also remind you, so remember, the integral of the cosine of kx dx, k is a constant, so if I'm taking the integral of cosine of 2x, derivative of what gives you cosine? Sine. So it'd be sine of kx. But if I was taking the derivative right now, I'd have to multiply by k because of chain rule. So since I'm going backwards, instead of multiplying by k, I'm going to divide by k plus c. And similarly, the integral of sine of kx dx is equal to the derivative of what gives you sine? Negative cosine. So negative cosine of kx over k plus c. So again, if I was taking the integral of cosine of 2x, it would just be sine of 2x over 2. So these pieces are pretty easy to take the integral of. Okay, so let's see how to use these. Evaluate. Let's do the integral of sine squared of x dx. Okay, when I see a squared, I could do 1 minus cosine squared, but if I did what I did yesterday, and I put in 1 minus cosine squared, there's no leftover piece for my u sub, so I'd get stuck. So what I can do instead, when I see a squared, is I can use the double angle identity. Okay, so this is the same as the integral of what we just did right here. Sine squared of x is 1/2 times 1 minus cosine of 2x. dx. Now when I say use the double angle identity, we're really not going to be using these ones over here. It's these ones in red that I got to that we're going to be using. So the 1/2 is just a constant. We can pull that out front. That's why I wrote it that way. So 1/2 times the integral of 1 minus cosine of 2x dx. And now this isn't hard to take the integral of at all. We've got the 1/2 out front. The derivative of what gives you 1, x. And then derivative of what gives you cosine, sine. So it'd just be minus sine of 2x over 2 plus c. The plus c is just a constant, so it doesn't need to get multiplied by the 1/2 because it would still be a constant. But when I distribute the 1/2 through to the rest of it, we end up with x over 2 minus sine of 2x over 4 plus c. So in some ways, this might be a little bit easier than yesterday's notes because I didn't even need any u sub once I did that. All right, I don't think it should be any big surprise that the integral of cosine squared of x should be the same. Let's try it. The integral of cosine squared of x dx. So again, I see a squared in here. When you see a squared, you want to use the double angle identity. So we're going to replace cosine squared of x with 1/2 cosine of 2x plus 1. That 1/2 is a constant. I'm just going to pull that out right away. So 1/2 times the integral of cosine of 2x plus 1 dx, which is just going to be 1/2 times the derivative of what gives you cosine, sine again. So sine of 2x over 2 plus x plus c. Then put the 1/2 through. So we have sine of 2x over 4 plus x over 2 plus c. Ease peas. So you just have to recognize what to do. If there's a squared involved, we're going to use one of these new double angle identities. All right, now just when you think life is good, I'm going to give you one more example. And it's a bad sign if I flip the page, because that means we need a new page for this last example. All right, so number 3. Let's do the integral of sine to the 4th of x dx. Okay, so the new thing I showed you today was that we could replace sine squared and cosine squared with these double angle identities. This is sine to the 4th. How could I rewrite that as sine squared? Right, I could just do the integral of sine squared of x squared dx. Sorry, that's not coming out as well on this page. That's a squared there. Okay, so then sine squared here is where you'd use your double angle identity. So this is the integral of, and you always need to flip back and check, sine squared is 1/2 times 1 minus cosine of 2x. So I'm going to leave the 1/2 in for now. 1/2 times 1 minus cosine of 2x. Okay, so that's all being squared, dx. Watch your parentheses. This piece inside the squared, sine squared of x, is all right here. All right, so what number could I pull out front? You could pull a 1/4 out front, right? Because 1/2 squared, the squared is getting distributed, would be 1/4. I'm going to leave the integral here for a second. 1/4 times the integral of 1 minus cosine of 2x squared dx. What do you think I need to do with this inside piece? Yeah, unfortunately I need to actually square it out. So if that's tricky, use a box. 1 minus cosine of 2x. 1 minus cosine of 2x. That would give us 1 minus cosine of 2x minus cosine of 2x plus cosine squared of 2x. Okay, so this is 1/4 times the integral of 1 minus, this would be 2 cosine of 2x plus cosine squared 2x dx. All right, now most of this is all fine and good. I can take the integral of 1. I can take the integral of cosine of 2x. 2 is just a constant. But what did I do when I had cosine squared? Well, with cosine squared, I replaced it with that identity. But that's when it was cosine squared of x. This is cosine squared of 2x. So look what's going to happen. If I had cosine squared, you don't have to write this down. If I had cosine squared of 2x, well, there would just be another 2 here. This would turn into cosine of 2 times 2x, or 4x. Okay, so if the thing inside is more than just x, 2x, you got to account for that over here too. All right, so this is going to become 1/4 times the integral of 1 minus 2 cosine of 2x plus, now cosine squared of 2x again. This is another double angle identity. So it's going to be plus 1/2 times cosine of 2 times 2x, which is 4x, plus 1 dx. Isn't this getting fun? So this is 1/4 times the integral of 1 minus 2 cosine of 2x plus 1/2 cosine of 4x plus 1/2 dx. And finally, before I take the integral, there's a couple like terms I can do. I can do 1 plus a half. What's 1 plus a half? 1/2 or 3/2. So finally I have 1/4 times the integral of 3/2 minus 2 cosine of 2x plus 1/2 cosine of 4x dx. And after all of that, I've got something I can take the integral of. It's 1/4 times 3/2 becomes 3/2 x minus 2 times cosine. Oops, derivative of what gives you cosine? Sine, right? So sine of 2x over 2 plus 1/2 times, what's the integral of cosine of 4x? Sine of 4x over 4 plus c. There's a lot going on here. The 2's cancel here. So I have 1/4 times 3/2 x minus sine of 2x. If I multiply this 1/2 in, it's a plus sine of 4x over 8 plus c. And finally, I can distribute that 1/4 through. So it's going to be 3/8 x minus sine of 2x over 4 plus sine of 4x over 32 plus c. How fun was that? You'll love doing that on the homework. So there's a lot going on. It's not tricky. Just work slowly and show all of your work. All right, so let's summarize. Yesterday we did sine to an odd power or cosine to an odd power. Today in general, if you have the integral of sine to an even power of x dx, or if you have the integral of sine to the odd power of x dx, you're going to want to change that. And you're going to change it into the integral of sine squared of x to whatever the remaining power is, dx, or you're going to change it to the integral of, oops, I do the same exact thing every time. Sorry, this isn't sine to the odd. This is cosine to the even. We're talking about even powers today. Stop complaining. Everyone makes mistakes. Okay, so if you have sine to the even power or cosine to the even power, this is what you do. You change this to cosine squared to the x, again to the remaining power. Dx. And once you've got that, when you have a sine squared or a cosine squared, you can use the double angle identity. All right, and that's exactly what we did on this big monster problem right here. I believe it was sine to an even, right? So I made it sine squared, and the remaining power was 2. But if it was sine to the 6th, you could have done sine squared to the 3rd, and it would have been even more fun. Okay? All right, so that's day 2. If you want to go to that worksheet that we're doing, I told you yesterday you could do 1, 2, and 4. Now you can do this cosine to an even power, and it's going to be very similar to that last example I did, so follow that through. So at this point, the only ones you can't do on this sheet are the last 3. We'll cover those in tomorrow's video. Have fun.